Hello everyone, I welcome you all to my talk on bubble coalescence. This is a joint work done with Alec, Chan, Dominic, and Dadla. And here they are. So today we are going to talk about bubble coalescence in the context of electrolysis process. On a lab scale, what we have is electrolyte, which looks like this. And then there is an electrode over here and lying on a substrate. And in the electrolyte, we have the viscosity eta and density rho, and then a gas bubble appears, and the gas liquid surface tension is given by gamma, and this gas bubble has a radius r. Now this is the process as it looks like in the lab. So what you see is that a bubble is growing up, and then it creates these tiny droplets that you can see in the center. Did you see it? Did you notice the droplets inside the bubble and smaller bubbles under it? So in fact, this big bubble is sitting on a bubble carpet, as you can see over here. And then there's a lot of droplets that you can see inside this big bubble. So the question that we asked today is, how does electrolyte enter bubbles in the electrolysis? In fact, what we want to answer is, how do these droplets, which are inside this big bubble, enter at all? And for that, I'm going to use the simulation code Bacillus C by Stefan Poppenet and team. And all the codes used in this work are freely available on this GitHub repository. So the process has several control parameters. The important ones are the radius of the big bubble and the radius of the small bubble, as well as the distance of the south pole of the small bubble from the surface below over here. And then, of course, the density and viscosity of the bubble and the density and viscosity of the surrounding medium, that is the electrolyte. With these properties, we can define several dimensionless parameters. One of them is the Ohnesorg number of the surrounding or the solvent, which is given by this eta s over square root of rho s gamma r. Then there is the radius ratio between the big bubble, capital R, and the small bubble, small r. Note that the Ohnesorg number is based on the radius of the small bubble only. And then, of course, there is a dimensionless distance of the south pole of the small bubble from the substrate, and that's given by d over r. Also, we call it chi over here. And then, of course, there are two more control parameters. One is the density ratio between the bubble and the surrounding medium, and the Ohnesorg number of the bubble. In the context of this work, we can think of the Ohnesorg number as a dimensionless viscosity of the fluids. And then for this work throughout, we're going to keep this density ratio constant at 1e minus 3. So to mimic air-water system. And similarly, we are going to keep the ratio of the Ohnesorg numbers also constant at 0.01, again to mimic air-water systems. So let us first start with bulk bubbles. What do we mean by bulk bubbles? For bulk bubbles, the chi, which was the distance of the south pole of the small bubble from the substrate, is infinity. And then we have only two control parameters. One is the Ohnesorg number of the solvent or the surrounding medium, and the radius ratio, RR. So in the parameter space of the Ohnesorg versus the radius ratio, let's just look at one particular case, which is over here, which has a radius ratio of 2 and Ohnesorg number of 0.08. 0.008, sorry. So here on this side, you will see the experiments, and on this side, you will see the simulations. In all the simulation videos, the left-hand side panel will show the viscous dissipation function on a log 10 scale. We do it on a log 10 scale in order to distinguish regions of high viscous dissipation given by black and the regions of low viscous dissipation given by white. And on the right-hand side, we are plotting the velocity normalized by the inertial capillary velocity. And so dark blue means high velocities and white means zero velocities. Now let us dig in. So first thing that we notice is the remarkable agreement between the experiment and the simulations. I will show this one more time. Isn't it amazing that we are able to capture the entire process one-to-one, including the detachment of the two droplets and how these droplets go up inside the big bubble. Note that there are some minor discrepancies between the velocities of the droplet that is ejected, and that is most likely due to the difference in the viscosity ratios in the two cases, because we don't know exactly what the viscosity ratio is in the experiments. So once we know these how these droplets are formed, the question is, how do we inhibit these droplets? And there are two ways of doing that. One is through viscous dissipation, and the second is through the symmetry of the problem. So let us first look at the viscous dissipation case. So now I'm showing you one extra case. So the case on the left, which is the radius ratio of 2. So both of them have the radius ratio of 2. And in the case on the left, the Onizog number is 0.008, same as the case I showed you before. And on the right-hand side, the Onizog number is 0.02, which is the new case, which is in fact slightly more viscous than the first case. It's in fact, yeah, it's roughly 2.5 times more viscous than the previous case. So it's over here in the parameter space, and you can see that for the case on the right, there are no droplets. So in fact, the viscous dissipation inhibits the formation of this jet and the formation of droplets as very nicely, as you can see very nicely over here. Now the second way is using the symmetry of the system. So if we keep the Ornithorpe number fixed, but change the radius ratio to 1. So that's the case on the right hand side. Okay, once again, the case on the left hand side is the same as the control case I showed you earlier, where we compare it directly with experiments. And now we showed another case, which is with the radius ratio of 1. And you can see over here that there are no droplets in this case. So simply there are two bubbles which would coalesce with each other. There are capillary waves that form, but it doesn't go any further. I should, of course, also talk about the mechanism. So let us go back to this proof of concept video. So here what we see is at the point of coalescence, when the two bubbles meet, so we have a small bubble over here and a big bubble over there. And when they meet, there is singularity at the point of contact, which is where the neck forms. And as this neck grows, there are several capillary waves that are formed on the surface of the small bubble. All these capillary waves meet at the south pole of the bubble. And then from there, we have a Worthington jet that forms, and this jet breaks into droplets, as you can see over here. Now, this process is quite peculiar in the sense that these waves are also simultaneously damped because of viscous dissipation. And what creates these jets is the capillary wave, which has the strongest, which is the strongest, which has the largest curvature, which is not damped out by viscosity, because of course viscosity will damp out the waves which have very high curvatures, but there would be one wave which is left, which has the highest curvature and is still not damped by viscosity. And the velocity and all the processes in this bursting world process is controlled by that wave, the strongest wave, which cannot be dissipated by viscosity. Okay, all right. So I showed you the mechanism, then I showed you the two ways to inhibit. Now let us look at all the cases in together. So now here is the regime map, which has over 1,000 simulations, which we now interpret as a classifying mechanism between droplets and no droplets, and that's the line that classifies the two cases. And as you can see over here, we have some cases where there are no droplets, and those are the cases with large viscosities, or the cases which have radius ratios close to 1. Those are this pink region over here. And then we have, of course, the droplets that are graded. That's in the blue region over here, which are for small enough viscosities and for several ranges of radius ratios. In fact, what you can see over here is that in the limit of radius ratio going to infinity, that's this value is greater than 10, for example, in this case, we notice that the on a critical Onizog number goes to a constant value. It doesn't change anymore with the radius ratio. And that critical Onizog number is that of the Onizog number for a champagne bubble, in fact. So we can also look at the experiments over here, and these are all the experimental data. And you see there is a very nice agreement between the experiments and the simulations. And of course, as I mentioned, the critical Ohnesorg number in the limit of radius capital R, much greater than small r, it goes to a constant value, which is 0.0325. And this is what several of our colleagues have also shown. And this is also what we see in the case of champagne bubbles. In the limit of capital R much larger than small r, we notice that the critical Ohnesorg number is around 0.0325. Okay, now once we know the classifying mechanism between droplets and no droplets, we would also like to know what is the size of the first injected drop. And for that, in the limit of capital R much larger than small r, we know that the theory which is true is this theory from Blanco, Rodriguez, and Gordio, which has given this very nice formula, which is over here, which has one fitting parameter, which is alpha, which controls the size of the droplets at 0 Ohnesorg number, and then we have the critical Ohnesorg number after which there are no droplets. And as we go to as we decrease the size ratio from infinity to, let's say, 16, we still get the same behavior. So the data points are in fact right on top of each other. And then as we decrease it further, then we see that the size of the droplet decreases quite a bit. So this was the regime map I showed you before, which classifies droplets and no droplets, both from experiments as well as from simulations. Now what we can do is we can look at this radius of the droplets on this using the same set of experiment simulations as I showed you before. And we notice that indeed for radius ratios of quite infinity, the size of the droplets are the highest, which is over here on the bottom left, right corner of this graph. And as we move towards this drops to no drops transition line, which is this black line over here, the droplets they become small and then they disappear completely in this region of no droplets altogether. Now there's something curious that occurs, and the limit of capital R equals to small r, as you can see over here, where also the experiments and simulations don't agree that well. And this is due to the fact that in experiments, there is always asymmetry because of the presence of needle or whatever. And then we noticed that there is this another interesting aspect of this limit of r capital R equals small r is the fact that there even at the radius ratio of 1, there is a finite critical Ohnesorg number, which is roughly 0.004 or something over here. Uh, and it's not it's not zero. So even the droplets can form even if the radius ratio is exactly 1, which is over here, if the Ohnesorg number is quite small. And we can show it over here in this video. So we have now two cases, both symmetric. So both have the radius ratio of 1. And in one case, the Ohnesorg number is 0.008. So this, by the way, is the same control case I have shown you before. And then we have another case, which is 0.004, which is half the viscosity of the first one. And you will notice over here that indeed this second case creates a droplet, which you see over here. And this in fact also explains why even if there is a symmetry, there is still a droplet, and that's because both these bubbles lead to the formation of a jet, which breaks into a droplet. This is different than a Worthington jet, as we have seen in the slides before, because in that case, the droplet that is created is from the Worthington jet, and it has a tendency to go to one side because of the size asymmetry. But if the sizes are symmetric, you can still get a droplet which comes out of both bubbles, of course. And this is non-trivial, but this can also happen sometimes. Okay, before I end, there's one more thing, because then we said, okay, why don't we go back to the experiments and compare the experiments that I showed you in the first slide, which was for the case of a bubble sitting on a carpet. And there you can notice that, well, if we start doing these experiments, and we start with somewhere over here, so so the time goes like this, and then as the bubble grows, the radius ratio increases, and so does the Ohnesorg number of the small bubble, because the small bubble size gets decreases as well. And then as you can see that the transition from droplets to no droplets occurs at around 0.05. And of course, this is very different than the value of 0.00325 as I have discussed earlier for bulk bubble. So what's going on? So intuitively, you would have thought that if the bubbles which were in the bulk, so which were far away from the surface, if their critical Ohnesorg number is 0.0325, then the critical Ohnesorg number for the other bubbles which are at the surface must have been lower, because there, of course, you have more viscous dissipation because of the presence of this lubrication layer between the small bubble and the surface. But that's not what we see. And the reason we don't see that, so the question is what went wrong? And so for that, let's look at the rule of confinement. So now, instead of looking at chi, which was infinity, we'll look at chi, which is 0. So basically the small bubble is exactly at the surface over here. And then so we have two cases. So now this is the radius ratio of 6, and the one is the Ohnesorg number of 0.005. And then in the case of infinitely far away, there is no droplet, whereas in the case where the bubble is at the surface, there is indeed a droplet, as you can see over here. And the mechanism is not that of viscous dissipation, but rather because of the reflective flow that comes in from the wall. So the difference between the left and the right again is that there is a wall in the right case over here. And then what happens is that you have all of this liquid that undergoes flow focusing because of the capillary waves. And then in one case where there is no wall, the liquid below simply goes away over here. So because, well, there is unbounded. Whereas in the second case, because of momentum conservation, the liquid cannot go down, so it comes back and it feeds into this jet. So it's an inertial process, and that's why the Ohnesorg number, instead of decreasing, that you would have expected because of viscous dissipation, uh, increase as there is a wall over here. In this case, in fact, the critical Ohnesorg number increases, and quite a bit. So it increases by almost a factor of 2. And this happens because of the reflective flow coming in from this substrate, which is non-trivial, which is not because of viscous dissipation, but because of the inertial flow focusing which occurs over here. Okay, so with that, I would like to summarize the results. So the question, how does the electrolyte enter electrolytically generated bubbles? Well, the answer is through Worthington jet, which forms when the capillary waves which were traveling post singularity from the neck region reaches the south pole, then creates a Worthington jet, which then breaks because of Rayleigh-Plateau type of instability and creates droplets. And then in this process, the radius ratio and the Ohnesorg number dictate the size of the first injected drop, and also it dictates when the droplets will form and when the droplets will not form, as shown in the two Rizzi maps that I have shown during this talk. And of course, the confinement matters, and it matters in a counterintuitive way. So when you bring the system close to the wall, instead of decreasing the critical Ohnesorg number, as one would have expected because of an enhancement in viscous dissipation, what occurs is that there is a reflective flow from the wall, and that feeds into the Worthington jet, which in fact makes the jet stronger, and which then further breaks into droplets. So in fact, it increases the critical Ohnesorg number until which we would get droplets. And that's why for the case of carpet coalescence with the big bubble, we still get droplets even for large Ohnesorg numbers. So with that, I would like to conclude this talk, and I'll leave you with this very nice comparison between experiments and simulations on the right.